Hello everyone, my name is Philippe Milot. I'm a developer at AudioKinetic in Montreal. And we're known for one thing, it's the Wwise audio middleware for games. And it's the proverbial big pile of C++ that you probably want to run on the web. So I'm here to talk about our attempt to make it run on the web, the obstacles that we encountered, how we worked around them, because we expect that the process for porting a big game to C++ is going to be very similar to what we experienced. So this work happened like 2 or 3 months ago. It's on a very recent version of Emscripten. So let's get started. First of all, just for those who don't know, what is Wwise? It comes in 2 parts. The first is an authoring tool, Mac and Windows application that is used by sound designers to basically create the audio structure of the game. So they list the events that the game will trigger and what kind of audio response should happen, from mixing, advanced effects, LPF, everything. And this authoring tool then generates a series of files called sound banks, and these sound banks need to be packaged with the game. And the other big part of Wwise is an SDK, a C++ SDK, that is integrated in the game by the game programmers, either standalone or via a game engine like Unreal and Unity. And this SDK comes with a sound engine that can read the sound banks and actually execute the audio in the game. So I just want to take a moment to talk about why it's important that this kind of work occurs. If we want the web to become a major gaming platform, middleware is going to be very important. So Wwise is used on studios all over the world, big and small. We have indie games and AAA games launching with Wwise. It's very popular. There's been over 500 games shipping with Wwise in the last 5 years, and the pace is accelerating. And the reason why Wwise is so popular is because it's cross-platform. We support every gaming platform under the sun, every popular ones, from mobile OSs to high-powered consoles and PCs. We're starting to do VR and AR. So that's exactly why we are here today. It's to make sure that we can see that the web can become another one of these major gaming platforms, and we want to be there to help it grow that way. So our first attempt was just to make it play a sound. So what you're seeing on the right here is a screenshot of our integration demo. It's just a basic C++ program that's a stand-in for a game. It integrates our Wwise SDK, and it just presents a menu to trigger a series of events that showcase the features of Wwise. So our goal was just to port that to the web. And we chose our Linux port as a base because Emscripten provides a POSIX environment, so that's very similar to Linux, and also because our audio backend on Linux uses the SDL2 library, which Emscripten also provides. So we thought it would be a good fit. And immediately, we were hit with the usual suspects. WebAssembly is an architecture that's neither x86 nor ARM. So there were a couple of code paths in our code base that either assume one or the other, so we had to fix those. Also, at the time that we were working on this, there was mention in the Emscripten documentation about SSE emulation for SIMD, and we could never get that to work. And I believe that it was removed from the documentation a little bit later. So I think it was just a bad timing on our part, where we used a version of the SDK that had that feature already removed. So right now, there are paths in our code base that do not use the SIMD implementations. They use a serial implementation that hasn't been used in years. So, for example, our Vorbis decoder right now does not work on the web because it exercises code paths that are just ancient. Atomics, normally Wwise has an abstraction layer for atomic operations. And the Linux port of this abstraction layer did not work out of the box. There were some compiler intrinsics that we were using that caused linker errors. So we had to basically re-implement that layer just strictly for Emscripten, using Emscripten-specific functions. And finally, Emscripten ships with a pthreads implementation that does not behave like normal pthreads. Obviously, it's based on web workers internally, and that comes with a baggage that makes it very difficult to act like a real threading system. So that was by far our biggest blocker. Our first attempt basically ended up in a bunch of deadlocks. Just to explain that, this is a model of our default threading architecture for Wwise. You have an event manager thread that is the main workhorse of the sound engine. It reads game events from a queue and updates the internal state of the sound engine based on that, and then produces some audio samples that it places in a ring buffer. And then it goes back to sleep to allow the rest of the game to allow more CPU room for the rest of the game. And that thread can be woken up in many ways. There's an API call to wake it up manually from the main thread. But usually what happens is that you have a separate audio thread that works a bit differently on every platform. So for example, for Linux, we had the SDL callback that normally runs on a different thread. It just takes the audio output data and copies it to the hardware. And if the ring buffer runs low, it will wake up the event manager thread so that it can produce more audio data. So this part is very important because it acts as a kind of a heartbeat for the system. It's what keeps it alive. And this was very problematic for Emscripten because we found out that the SDL2 implementation in Emscripten is based on the old script processor node of web audio, which implied that the audio thread here was actually the same thread that you see above. They are not different. And this was coupled with the fact that our Wwise SDK comes with a series of blocking API calls for game developers. And by default, this is what integration demo used. So it calls for loading bank files, for example, and unloading them. Those are blocking calls that will only return when the event manager thread has processed the work. And I know you guys are web developers, and you're like, what, blocking on the main thread? No. But this was an exercise in measuring just how much friction C++ developers are going to encounter when porting to the web. So if the answer is only, oh, well, you use blocking calls, so sorry, it's never going to work. That's not good enough. So you want to reduce the friction as much as possible. And especially for us, we're middleware developers, so often the blame comes to us. Hey, you're deadlocking. Like, just fix your stuff. So it was very important for us to do better than that, even if the first attempt ends up not being optimal because there are blocking calls on the main thread, it should at least work, and then they can improve it from there. So we had to do better. For closing off our first attempt, we just ended up disabling all threading altogether and run everything on the main game loop just to avoid the deadlocks. So that worked, but obviously there's so little CPU headroom on the game loop that it basically makes it impossible for a real game to run. Especially there's no room for advanced audio effects, which makes it pointless to use Wwise. So we had to do much better than that. And that comes to our second attempt, which was to replace our SDL dependency with a custom sync that's made just for the web platform based on AudioWorklet and the Web Audio API. And that came with its own challenge because the AudioWorklet requires you to have a separate program similar to how a web worker works, that is completely closed off from the rest of the application. So the challenge became, how do we share the ring buffer that contains the audio output with this processor program? So we looked at how Emscripten was doing it for pthreads. We saw that they implemented it using web workers, obviously, which normally has the exact same challenge. So we saw that their worker file that is generated by Emscripten actually imports the main app module And this app module is written in such a way that it can detect which environment it's being imported from and export different things based on that. So that's the way that they were able to access the WASM heap from the web workers. So we thought, that's great. Let's just do the exact same thing. So we did that. From our processor program, we imported the main game module. And of course, that did not work at all, with only a vague error about promise being rejected with no further detail. So it could be anything from a syntax error in the processor.js to what we had, which was actually that the main program that is the main GS file that is generated by Emscripten uses APIs that are not supported by AudioWorklet global scope. So there was an internal error which made the promise reject. So it took us a long time to figure that out, why it wasn't working. And we made some more research, and we found out that if we compile it to an ES6 module instead, if we compile the main application as an ES6 self-contained module, then AudioWorklet can import it. So we did that. There was an option in Emscripten to do that. And yeah, the AudioWorklet was able to import it. However, the worker global scope does not support importing an ES6 module. So we kind of had this catch-22 where it's either one or the other. You choose which one you want to break, AudioWorklet or pthreads. So that's no good. So what we ended up doing was something much simpler. We probably should have started with that, but that's the nature of researching and experimenting. Our processor program, instead of importing anything, gets initialized with a post message that contains a reference to the WASM heap directly, along with a bunch of pointers, raw pointers pointing directly to the audio buffers that it needs with their size and everything. And with that information, well, the processor program can build its own views on the data and work from there. So that works as long as the WASM heap does not change during the course of execution. So once we did that, it worked. We had like a separate heartbeat, a separate thread, and we were able to re-enable all threading, the event manager thread, the bank manager thread, and we actually had a working system, no deadlocks, and we had sound. Spatial audio was working as well. Many of our effects are software effects, so as long as we can actually execute the code, it works. So we were very happy about that. So in retrospect, AudioWorklet, major improvement over script processor node. I know that's old news, but I just want to reiterate. Also, throughout our process, we never actually had any audio issues. We just needed to learn the APIs, the environments that Emscripten provides, the warts, how to work around them. But it's the same process that we use for all of the other platforms that we support. So we were used to that process. The bad, well, like I said, threading is very difficult to get right. From the point of view of a C++ developer, the pthreads abstraction is so different that it's going to create a lot of problems. Also, the debugging experience was non-existent for us. Emscripten failed to properly build source maps for our C++ code because of the structure of our projects. And so we were down to doing printf debugging throughout this whole thing. It was extremely painful. And we are convinced that if only we had access to a proper debugger, we could have accomplished so much in the time that we had. And finally, AudioWorklet is great, but it's meant to work as a node, as part of a larger graph. It's very high level. We kind of wish that there was a lower level API that would let us do things like control the number of samples per frame and actually perform the final audio processing before it's sent to the hardware, like channel interleaving, the final channel downmix, stuff like that. So right now, it's not possible with AudioWorklet. It's not a deal breaker, but it could be optimized for performance reasons. And on that note, there's the new audio device client that we're going to hear about from Hong Chan next. That looks very, very promising for us. And finally, there's a good, a bad, and a ugly. Shared array buffer. I need to reiterate again and sound like a broken record that we need this. If you want C++ games to run on the web, this problem needs to be fixed, because if there is no threaded, there is no AAA games running on the web. And we were really happy to hear that Mozilla seems to finally have a solution in the near future. But what about Safari? What about mobile browsers? It seems like there's still a lot of work to be done here, and I want people to be as nervous as this as I am. And let's remember that what we want to support is a platform called the web, not just Chrome. And we don't want to go back to the days where we have this button at the bottom of the page that says, best viewed on browser X. We don't want to go back to those days. So let's work on making that much better. So that's it for me. I hope that helped build empathy for us poor C++ developers. Thank you very much.